Hi. So you guys know that this is a wave right over here. I know it's not the prettiest waves. And the top of like a wave or a hill, I like to think of them, is called the crest. And then the bottom part, and it goes back down, it's called the trough. And this axis of propagation, wherever the axis of propagation is where we would measure the amplitude, which is the height of a wave from the axis of propagation. So if the axis of propagation was over here, then the amplitude would be starting from here and then you'd go up, or you would go down. But if the axis of propagation was like over here on the bottom, then the amplitude would be from here to there. And the node is the place where the amplitude is 0. So it's right here, which is always going to be on the axis of propagation. And this is a wavelength. The wavelength is when you if you started at this point and then you went all the way over here and you started at that point, what's the length between your 2 points, which defines the length of a wave. And the symbol of a wavelength is lambda, and it looks like this. And the unit for wavelength is usually in nanometers. And the frequency is basically the number of hills, like how frequently do you see waves in this amount of this section. That's the number of waves basically. And its symbol is V. Don't get it confused with velocity. I know it's a bit confusing sometimes. And hertz is the unit that frequency is measured by. So, electromagnetic radiation is energy. And it's a type of energy that can travel in a vacuum. In a vacuum, just to recap, an area that is completely empty of any form of matter, such as plasma, gas, liquid, solids. Okay, so it's that type of energy. And there's many different types of electromagnetic radiation. There's UV, gamma rays, microwave, X-rays, all those types of energies is electromagnetic radiation, including light that we can see. That is electromagnetic radiation. It is electrical and magnetic at the same time, and its electrical and magnetic properties are perpendicular to each other. So the electromagnetic radiation kind of looks like this. It looks like a wave, and then the electrical and magnetic, so one of them is going this way and the other one is going this way. It's like exactly perpendicular to each other, like 90 degrees. So that's how it kind of looks like. So when we have, this is quite an important equation that we need to know. When you have a wavelength, speed equals wavelength times frequency. And when we're talking about electromagnetic radiation, it's basically the speed of light, which is c. And the speed of light, it's a constant. No matter what type of light you have, it's always going to travel at this speed right here. Okay? And so if you have the wavelength and you have the speed, you can just, because it's a constant, you can just rearrange it to find frequency and so on. Okay? But wavelength and frequency are inversely proportional. It means when you have the longer the waves, okay, so the more wavelength, the less waves there are, so the less frequency. So if wavelength is more, frequency will decrease. They're inversely proportional. It's not like when one increases, the other increases. No, when one increases, the other decreases. So the longer the wave, the less waves there are. The more waves there are, the shorter the waves. And this is just to give you a visual. See? So if the wavelength is short, less wavelength, more frequency. Look how many waves there are. Woo! Okay? And then if there's long wavelength, less frequency. There's not that many waves. So that's just an example. Okay, so there's this thing that looks all complicated, and it's called the quantization of energy. Okay, and basically this thing happened, and they called it the ultraviolet catastrophe. And this ultraviolet catastrophe is when this metal rod, this glowing metal rod, okay, so it was glowing. You could see the glowing light. It was glowing, and but the color of it wasn't what they thought it. Like, they were increasing the heat, but the emission of the color of the light was not what they expected, so they called it the ultraviolet catastrophe, because they didn't expect, because that color that they were expecting did not appear. And this is basically the range of different types of frequencies of electromagnetic rays. So from over here going all the way over here, this is increasing frequency. And this small section here of the types of electromagnetic waves, this part over here is the only types that we can actually see. And as you increase in frequency, you increase in energy. Okay, so these frequency energy is directly proportional. As one increases, the other increases. I mean, it makes sense. Like, if you had more waves, you obviously have more energy going on. Okay, and so they had this thing, they called it black body radiation. So black body radiation, a black body is, you know how like black, the color black, absorbs all light and so on. So basically that's why they call it black body, because black body is any object that absorbs all the colors, which means all the light. I mean, all the electromagnetic rays, all the types of it. It absorbs everything, okay? And it absorbs everything, basically. So it was described as black body radiation. And so what happened is, this guy called Planck, he explained the ultraviolet catastrophe and the black body radiation with this theory of quantization, which I will explain. Just give me a second. Okay, so he explained here, remember about the proportional part? Okay, proportional part. So he put an equation for that. He said energy equals this constant times frequency. Okay, and this constant, this is an important equation, by the way. This constant, it's right here. They'll give it to you. Don't worry about memorizing it. He came up with it to convert and relate the number of waves, which is frequency, with the amount of energy. Like, you know how, for example, like the constant that we have to convert feet into inches, like, this constant right here. I mean, when you have 2 feet times this constant, that for every 2 inches it is 1 foot. So it's kind of the same thing here. He came up with this constant to, if we have the number of frequencies, if we had a certain amount of frequency, he used this constant to convert the amount of frequency to how much energy is actually that amount of frequency. So he used that, and he used that to explain something. Okay, he said that the level of energy / frequency rate, like, like gamma rays, like that, the different level or type of energy and frequency will not change except when a certain amount, if there is a minimum rate, a certain amount of energy and energy / type of frequency is given. And this certain amount that is necessary for this change, it comes in it's like a packet of energy. It's a certain amount. It's a packet, and it is called a quantum energy. So he uses to kind of explain what happened in the the ultraviolet catastrophe. So what was happening was that, you know, as they were increasing the heat of this metal rod, this glowing metal rod, they were increasing either that they were increasing the energy, increasing the heat, and increasing the frequency so much that after a certain amount of time of collecting this frequency, that it got this packet, this quantum of energy that made it jump to the ultraviolet frequency area of the electromagnetic radiation. And as you can see, this part of the electromagnetic radiation called ultraviolet, it is not in our visible spectrum. Its frequency is way too high for our eyes to see. And it's either that or the fact that the metal rod didn't get that quantum energy that it needed, that packet of energy that it needed to jump from visible light to ultraviolet light. So he used the quantum energy to explain that. And so basically, like, the energy here cannot change unless if you have a certain amount of a certain type of frequency. Like if you have really, really, really high frequency, and that's what causes a certain type of energy to occur. Like the change of energy to occur, you need this specific type of frequency. So if you knew that maybe the gamma rays has this certain type of frequency rate for the gamma rays, and if you wanted to change to get something to emit gamma rays or absorb gamma rays, then you would need this amount of energy. So you can use this equation to calculate that, because they are proportional, as we explained before. So there's two formulas that we can put together. Remember the one that we just talked about now, how energy is proportional to velocity to frequency using the constant. And remember, in the first place, we talked about how speed is lambda times the speed of light is lambda times the frequency. So we got this equation by putting them together. I'll show you how algebraically. Okay, so if E equals h times v, and we have here c equals lambda times v, and we could just rearrange this to isolate v, to know what v is according to this equation, and v is c over lambda. So we go back to this equation right here, and we would just use this as a substitute for v, because it equals v, so we can just put it here. So E equals h times v is the same thing as E equals h times c over lambda, and that gives us this part right here, gives us this part. So putting these two equations together, this is what we got. So this combination of two formulas together, the good thing about it is, because we have the constant c is like a constant, we know it, and h is a constant, we know. And so the good thing about this is that if we had frequency, if we had any one of these three, okay, we can find any other one of them. Like if I had wavelength, I can just plug it into this equation, and if I had wavelength and I wanted to find frequency, I can use this equation to do that. I don't need a wavelength and energy to find frequency. And so that's the good thing about it. You only need one of these to find the other. You can just, if you had energy, you can find frequency or wavelength. Okay, so that's the good thing about this combination equation. Moving on. So you might have heard of the dual nature of light. Well, let me explain what happened. So, Einstein in his famous equation of E equals mc squared, how mass is always moving and it has energy because it's always moving. Remember this part? Okay, so let me just explain what happened. So, they rearranged this equation and they isolated m. So, m equals E over c squared. And then they remember how E right here is this, right? E equals this here. So they put it back here. They were like, okay, let me substitute E with this. So they put E equals h times c over y over c squared. And then the c cancels out. This becomes a 1. And this goes to the denominator, so it equals to h over c lambda, c times lambda. So what happened here? They were like, okay, wait, so if energy is light, you know how energy is light, we talked about it, when we were talking about electromagnetic radiation, which is light. It's actually energy. So if energy is light, and energy is moving mass, then light has mass, because if these two together are energy, and that means light, the wave-like thing that we know as light, it actually has mass to be energy. And if it has mass, then it means it has the particle like property. So it has both the wave-like and particle-like properties. And so the light, they made it known as that the light is made out of particles called photons. So not only is light a wave, it is photons. It is also particles called photons. And then what also happened, they were like, okay, so if light could be the wave-like light that we know is also particles, does that mean that the particles that we know are also wave-like? And it actually does make sense, because but using the equations, look at here how m equals the mass equals to this part right here, and this part right here has lambda, and lambda is wavelength. So it means that mass has wavelength, and mass is made out of particles. So particles have wave-like particles. So it's not. So they both ended up having two properties. That particles are now, that mass has particle-like properties and wave-like properties, and light has wave-like properties and particle properties. And so if we wanted to find, for example, the wavelength of a certain type of mass, we can just rearrange this equation. Instead of using the speed of light, we would just change it to the speed, the velocity of the mass, and we can use that. So that is the dual nature of light. The light is not just a wave, it is also particles and photons. So we're going to use our newfound knowledge about photons to explain, to use quantization and our new knowledge about photons to explain something else. So Einstein was like, he found out this thing called the photoelectric effect. And to remember the meaning of the photoelectric effect, I like to think that, photos like light, and, photons and energy. Photons is energy and light is energy, so that's how I remember something. And electric is like electrons. So the photoelectric effect is actually when you hit an atom with a quantum of energy, which is the right frequency rate. And quantum of energy is, light, and they hit it with an amount of light, and light is energy. So they meant it with a quantum amount of energy, or the right type of frequency rate, and the electron's energy increases, and the electron gets excited, and it actually gets ejected out of the atom itself. So he used the knowledge about photons and the quantums to explain atoms getting ejected because they got the right amount of quantum energy, and they were, yeah. And then, so we're going to move on now, and how quantums were also used to explain absorption and emission of energy and light and color, using the Bohr model of the atom. So we're going to go a bit deeper now. So we have, this is the continuous spectrum of the colors of the visible colors that we can see. This is a continuous spectrum. So what ends up happening is that you give the electron the electron gets a certain amount of energy and a certain frequency, and this certain amount of energy and certain frequency is absorbed. Okay, so what ends up happening is, like, okay, if this is our model of our atom, and our electron is right over here, so it needs a certain quantum of energy to absorb, and when it absorbs it, it gets excited, and the energy of the electron increases, and it jumps up till here. And when it jumps up till here, it has absorbed, for example, this amount of frequency here, and it can jump back down. And if it jumps back down, it is like releasing energy, and it releases the same amount of energy that it absorbed. Therefore, that's why we see here a black spot. The black line here is the frequency that it absorbed, and so the emission spectrum is the exact opposite of it. Is that this line here is the energy that it released when it jumped back down. So when it jumped back down, it emitted this frequency, this light that it actually absorbed in the first place. But if, for example, we went from, the electron was over here and then jumped all the way over here, it absorbed probably one of these high frequencies, which is a large amount of energy, because you need a large amount of energy to do that. So, and then probably when it jumps back down, maybe going there, it emitted whatever it absorbed. Like if it absorbed this frequency, it emits the frequency that it absorbed, and so on. So what ends up happening is, this is really useful because each atom and element has a different emission spectrum, a different absorption spectrum. So electrons, if there's like more electrons, they jump around more. Like an electron could go all the way over here and then maybe jump back down here, but then it could also go all the way over there, maybe jump back down here, maybe all the way over there, and then jump back down here to the first place. So it can do a lot of jumping around, and a lot of absorbing and emitting, and each element has different pattern of absorbing and emitting. It has different amount of electrons and different sizes and so on. So it's like a fingerprint, an identity, as they describe it. This emission spectrum and absorption spectrum, and absorption spectrum. Yeah. And so this is very important when we're talking about quantum energy, because you need a certain amount of frequency. Like if you give it less than the amount that is needed, it's not going to do anything. The electron is not going to move from its place. But once you hit the minimum amount that it needs, that certain quantum of energy, that okay, I have enough energy now to jump. That's when it's a quantum. Like so that's an important. So they used it now, and here's another diagram to explain it. So if it goes all the way up there, and it's up there, and when it goes from an excited state to lower state or ground state, that's when that's when it emits energy, and when it emits energy, it comes as light. So the only emitting released light that we actually see is when it's from whatever excited orbital to only the second shell, the second orbital is what we actually see. That's the actual visible light that we see. And they call that the Balmer series. That's why it's actually colored. They call that the Balmer series. The other ones we don't actually see. Like, for example, this one has more frequency, and it's probably the ultraviolet rays. And this one is probably the with the less frequency. But we only see this frequency, this amount of energy that was emitted, because we don't see all the electromagnetic radiation. Our eyes do not view all types of frequencies. And yeah, so to find out the quantum energy of each jumping down or jumping back up, to find this from here to here, this how much energy, this quantum energy, how much energy do you need to jump from here to go to there? And how much energy is released when you jump back down? So to find that, Bohr came up with this equation, which is energy equals to this constant, and they're going to give you the constants, don't worry about it, and this right here, which is Z is the atomic number, atomic charge of your element. Yeah, the nuclear charge. Wait, let me check. Yeah, it's the nuclear charge of your element. And then the bottom part is the shell that it was at, and then in the first place of where you're calculating from, and then this one right here, the denominator, is the initial this is where it was at the final place, and this was at the initial place. So like if this is the initial place that you started from here, and then you wanted to find out how much energy it took to jump to this place right here, this is your final. So this would be 3, and that would be 2. Okay, and don't forget that you have to square it. And yeah, so you put your nuclear charge up there, but as this equation it actually only works for hydrogen, so it's always gonna be 1 at the top. And yeah, so it's also going to be one at the top, so that doesn't really matter. Don't worry about the nuclear charge. And yeah, that's actually all you need to know about electromagnetic radiation and what's it called? And the atomic structure. And just know the 3 formulas that we talked about. This one and these 2 put together. This one right here, and this one right there, and this one. Those are the 3 that you need to know. And actually, don't forget, this is quite important, to note your units. Because, for example, if you're trying to find the frequency of a certain wavelength is usually in nanometers. And to find the frequency of the certain wavelength, if you rearrange this equation, you would get C over lambda equals V, right? And so you're going to have to use the nanometers down here, and then wait, the speed of light is meters per second. What's happening here? So your frequency would be wrong if you did that without converting this to nanometers. So you'd actually have to convert the speed of light to nanometers, or the what's it called? The unit for a wavelength into meters. But basically, you have to have the same units to get the right frequency answer.